Hey guys, Long here, back with another math video. Today we're going to be doing 2017 AMC 12B, problem 22. You might recognize this if you took the AMC 12 test. So without further ado, let's just get right into it. So read the question if you need to, pause the video and read the question. Try to solve it if you can. And I'm going to go into the solution. So the way I solved it on AMC 12B was I just straight bashed it, and I'm not one for very creative solutions, so though I think my solution is a bit tedious, I think it's a bit also pretty easy to understand. So I just completely bashed the total number of combinations of games that could happen. So let's see. There's a total of 4 games, and in each of those games a person gets either the red or green ball. Okay, it seems reasonable. Let's see how the total number let's first calculate the total number of combinations that could happen, since it asks for the probability. So let's first calculate how many total possible number of unique games could occur. So in each game, a person gets the green ball and a person gets the red ball, and the other 2 people just get the white balls. So if we determine who gets the green ball and the red ball, we just already know what happens in that game. So for each game, you choose a person to get the green ball, so that's 4. You can choose out of A, B, C, or D who gets the green ball. And then out of the remaining 3 people, you choose who gets the red ball. So that's 3. So in each game, there are 12 possible ways to choose who gets the green ball and the red ball. Now, since the other 2 people get the white ball, for each game, there's actually 12 possible ways how it could go. And since there are 4 games, that's just 12 to the 4th is total number of combinations. Now, that seems like a lot, 12 to the 4th. That's going to be the denominator of our probability. That's the total number of games, total number of possible unique game combinations that could occur. And yeah. So let's go on to the more difficult part, trying to actually bash what could happen such that no player loses any coins. And the 4 coins is sort of a red herring. You don't care that there are 4 coins. Basically what this is asking is, for every green ball any player has drawn, they also have to draw a red ball later on, so they don't gain any coins and they don't lose any coins. So essentially what this means is that if say person A gets a green ball in round 1, then on round 2, 3, or 4, they have to get a red ball to counteract their gainage. Similarly, if they get a green ball 2 rounds, they have to get a red ball the other 2 rounds. Essentially what that means is that that actually makes it sort of easy. It's just that if whoever appears in this line of getting green balls each game, they also have to reappear in getting the red ball each game. So now we have to just find the total number of ways this could happen. So there are 3 cases. Case 1 is that A, B, C, D, they all get a green ball in some rounds. And then they reappear and getting red balls in other games, and you have to first you have to calculate what is the number of ways we could rearrange this so that we can count the number of possible permutations of A, B, C, D getting green balls, because it could also be D, C, B, A, or B, C, A, D, right? So we have to count the number of ways, count the number of combinations and orderings that A, B, C, D get green balls in the 4 games. And that's just 4 factorial, right? You just rearrange these, it's just 4 factorial. And now we have to know for each of these possible arrangements, say this is one valid arrangement, A, B, C, D. For each of these arrangements, how many ways can we order them for these games such that A, B, C, D appears again later on to get red balls. So for instance, B, C, A, whoops, I did not, D, A, right? That's a possible way. So in game 1, A gets the green ball, B gets the red ball. Game 2, B gets the green ball, C gets the red ball, right? So each one of these appears again in another game getting a red ball to counteract their gainage when they got a green ball. So this is like case 1, right? And you have to be careful because this is not valid. Because you can't have A get a green ball and a red ball in one game at the same time, because he doesn't draw 2 balls. So really, we have to count the number of possible combinations that A, B, C, D can be arranged on this line, such that A is not under itself, B is not under itself, etc. And actually, you can just count them by hand, really. So for B, if B is under A, if B is under A, then you know, A could be here, and then you have to do this, so that's 1. And then other than that, if it's C, then it's DA, that's another one. And then if it's D, you get AC, that's another one. And there and then it could be C here or D here. And for B, C, D, whichever one you put in this thing, you have 3 possible ways you could rearrange these. Really, it's not that hard to just count them out. That's what I did. You don't really have to like waste time trying to actually calculate it. You can just count them out, and there's actually 9 possible ways for you to arrange A, B, C, D on this line such that A isn't under itself, B isn't under itself, etc. So totally the number of ways for case 1 is that there are 4 factorial possible ways to arrange A, B, C, D on the top line, and for each of those arrangements there are 9 possible ways to arrange the bottom for A, B, C, D. So that's 4 factorial times 9, which is, I'll just leave it like that. Case 2 is if A, B, D, and red. So we just do the same thing, except now we have to keep in mind, we have to be careful here. First we calculate the number of ways we could rearrange this, so that's 4 factorial divided by 2 because there are 2 duplicate A's, and that's just 12. How many ways can you arrange the bottom? Well, the bottom can be arranged, A has to go here. It has to be here, because it can't be here or else it'll be under itself, and B, D can be switched, D, B. So for any given ordering of the top, there's only 2 possible ways to arrange the bottom. That's this, and that's this. So that's 2. But we have to be careful, because 12 is only the number of ways we can arrange A, B, D. But now we have to consider that what if we chose C, D, or C, D, A, etc. We didn't need to consider it here because there was only one way to choose A, B, C, D out of A, B, C, D. You have to choose A, B, C, D, right? But in here you can choose which person gets 2 green balls, and here you can choose which person is left out and only gets white balls. So how many ways can we choose a set of 3 people and choose one of them to get 2 green balls? So that's simply 4 choose 3. You choose 3 people, you choose one to leave out, times 3, because out of those 3 people you can choose one guy to get 2 green balls. So that's just 12. So this ends up being 12 times 12 times 2. Case 3 is pretty simple. As you might have guessed, it's just A, B, B, and there's only one possible combination on the bottom. Okay, let's think about this. How many ways can we choose 2 people to actually get green balls? So that's 4 choose 2. You choose the 2 people to actually get green balls and red balls. So you can choose C, C, D, D, or A, D, D, etc. How many ways can you order the top? So it's like A, B, or B, A. Well, that's just 4 factorial divided by 2 times 2, which is 6. Yeah. And the bottom, there's only one arrangement, so that's times 1. Yeah, so that's all, every single case. You can't really have A be at the top, because then they have to like get the cases overlap, right? Like this, like A has to, if A gets 3 green balls, there's no way he can also get 3 red balls to counteract his gain. So these are the only cases that are possible. So I think that's right. If that's not right, tell me. But I just added up this, this, and this over 12 to the 4th. If you calculate that, you get 5 over 192. So that's the answer. I did it like with bashing. If you have more creative ways you can do that, I'm just I'm pretty bad at math, so I just did it. Bashing. Don't ever be afraid to bash, okay? Yeah, I hope you guys did well. Yeah, see you next week. The floor of x plus 1 has moved this over, which is actually also equal to, if you make this x